In this video, we will talk about some techniques that can help you solve a lot of bit manipulation problems, as well as a lot of problems related to dynamic programming on bit masks, SOSTP, submasks, and so on. So this video will be mostly focused around the concept of tight that exists in bit manipulation problem. And although it is very implicit in these kind of problems, but if you are a beginner to bit manipulation, you might not even understand what tight means whenever it is being referred to in an editorial. So the focus of this video will be talking about this tight concept, although we will start out with a problem that involves the application of this tight concept. So you can try out this problem on your own, and if you are not able to solve it, you can watch the rest of the video even if you do understand what tight means in the context of bit manipulation. Let's start with the problem description. You are given two integers n and k as an input. So the input is n and k, and you have to find the maximum sum of k integers. You have to maximize this sum by following these two constraints. What are the constraints? The first constraint is that the sum of those, that the XOR of those numbers should be equal to the given integer n, and as well as each of these integers should be less than or equal to n. So how do you compute the maximum sum? You don't need to find a valid sequence AI, but you do have to find what is the maximum possible sum if you choose each of your AI optimally. So how do you solve this problem? So you can start out by thinking that had this constraint not been there, let's say the XOR constraint wasn't there, only one constraint was available, then what is the maximum sum that you could theoretically achieve of k integers where each integer is less than or equal to n? So that maximum sum can only be achieved when you take n for each entry, right? So the maximum sum will be equal to k into n. So if this is the maximum sum, but now you are also added this constraint that their XOR should also be equal to n. Now, can you still achieve this maximum sum while still following this constraint? So if you remember the property of XOR, which is n XOR n is equal to 0. So XOR of identical number is equal to 0. So if there are a total of odd terms over here, there are total odd number over here, because there is another property of XOR which says that n XOR 0 is equal to n. So if there are an odd number of n's on the left hand side, then every consecutive pair will form a XOR as 0. Every consecutive pair forms a XOR 0, and the overall XOR becomes 0, and then finally 1n will be the lone n remaining, and you can still see that the XOR of this entire sequence is equal to n, just like we wanted. So this means that it is possible to achieve this upper bound k into n by smartly selecting AI as n for each AI. So no fancy bit manipulation tricks needed if n is odd. Now what if n is even? So how do you solve the problem in that case? So if n is even, then you still want to achieve your dream sum, which is this k into n, right? This is the maximum possible sum, but you know that you cannot achieve this exact sum, but you would like to be as close to this sum as possible. So let's start with how you would approach it. So if you are like, let's say 1500 rated or something on Codeforces, you might think that, okay, previously you were able to get a maximum sum by taking n in all the components, right? and only the last component, this remained, right? And that's why the sum was 0. But now if this last component is missing, then this sum of this entire, this XOR of this entire part is still 0, but you want to make it n. But if you just remove one element, what will happen? This sequence will become odd, and then the last element will be present over here. And if you want to maximize this segment, and you can maximize it by taking n in each of these slots. So their XOR will be equal to n. Why? Because this is an odd number of elements that are living over here. And then you can add a 0 over here. So you are still able to achieve close to the maximum, which is k minus 1 times n. You had to sacrifice one element. You had to set it to 0 so that you could still achieve the maximum in every element that you could. Now, of course, this is the first idea that comes to mind. And of course, this is not correct because this is kind of a greedy algorithm, and every greedy idea that you come up with might not necessarily be correct. So how do you approach this then? So then let's say if you are 1700 rated on Codeforces, how would you approach this? So you would realize that when we are splitting the numbers, right? And instead of creating XOR n over here and XOR 0 over here, so we are sacrificing this element to make this as k minus 1 block. But you don't have to sacrifice this element. In fact, you can increase this element and then decrease some other element to get some better XOR. So one correct strategy could be that you have, like, let's say this is n minus 2 numbers. So n was even. So what you do is you reserve two number over here, like let's say x and y. And for these n minus 2 integers, you know that you can still place maximum in all of them. You don't have to compromise any of these numbers. You can still place XOR in all of them, and the resulting answer is 0, right? This means that just from these two numbers, you have to create a XOR of n while maximizing their sum. So like, yeah, right now we are dealing with when you are, let's say 1700. So how would you do this, right? So you are looking to solve this problem that x XOR y should be equal to n, x should be less than equal to n, y should be less than equal to n, and you have to maximize x plus y. So okay, that's good that at least you got the idea what you need to do. But if you're 1700, you might not know how to solve this equation. Like, how do you maximize this? How do you maximize this sum when the XOR of two elements is fixed and x and y can be less than or equal to n? So you might not know the technique to solve this problem. But if you are, like, let's say rated 1800 on Codeforces, so you might know how to solve this kind of problem. The problem that we just discussed, which is x XOR y is equal to n, and you have to maximize x plus y given that x and y both are less than or equal to n. This is how your 1800 brain might work. And how would you solve this? So I will not dive into the solution of this, but I'll just give you an overview. So you might remember this famous identity, which is x plus y is equal to x XOR y plus 2 times x and y. So if you are higher rated, you might know this technique, and this value is fixed. So maximizing the LHS is equal to maximizing the RHS. So this maximizing X and Y, this is a known famous problem. Maximizing X and Y when X comma Y is less than or equal to N. There is a very standard trick to solve this problem, which I will not dive deep into in this video. Now all of these look pretty convincing, right? So at first you might realize that, okay, I'm very smart for figuring out that greedy does not work by giving all the load to the last element. So in fact, you will be pretty convinced that the ideal strategy is to split the load between these two elements and then give these two elements the maximum benefit that you can give. But actually this approach itself is wrong. This greedy idea that we just discussed, wherein you partition into n minus 2 and then take the load down these two elements to maximize the XOR, this actually is not the correct strategy. In fact, there is a better strategy if you distribute the load on all the elements. And this might seem very counterintuitive because greedy problems, whenever they arrive, they can convince you that, okay, this greedy is wrong, so this greedy might be correct. I am going in the correct direction, right? You might even draw out these fancy equations and you might convince yourself, I am heading into the correct direction, because maybe a hard level problem is indeed asking me for these techniques. So what is the counter example for this? So the counter example is consider n as 30 and k as equal to 4. You have to construct 4 elements. So your greedy strategy, I mean not so greedy strategy I should say, because you are applying the optimal strategies on these two elements, that's fine. So you will split 30 and 30 and x or y is equal to n. So the maximum that you could get is this 17 and 15 only, which turns out to be 32. And so the sum of this entire part is 92. But if you don't be greedy and you distribute the load in 29, 27, 23 and 15, you will see that their XOR is still 30 like before, but now their sum is 94. So now you can try out this counter example on paper to convince yourself why the greedy strategy, even greedy strategy for n-2 elements is not correct. You have to come up with an optimal strategy that distributes the load evenly between all of the elements but still maximizes the final sum. How do you do that though? So to do that, we'll now talk about the concept of tight. So let's consider any number in binary representation. Suppose the number is 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1. Now this is the number in binary, and your goal is simple: find all the numbers that are less than or equal to x. How do you do this? Now whatever number that you create, that will also have a binary representation. So in the number that you are creating, right, let's call that number lesser or less than or equal to, right, less or equal. What all values can it have at this bit position? Can it have a 1 over here? So I think the 90% of bit manipulation technique is centered around this idea that in your high school you must have learned about this famous equation wherein 2 to the power I minus 1 is equal to 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 up to 2 to the power I minus 1. So in fact, if you remove, even if you remove this equality and convert it to a minus, convert it to an inequality, the equation that you would get is 2 to the power I is strictly greater than 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 and so on. So I have already talked about this idea in my Brain Gym episode 4, But since this is the crucial observation in which every technique built on bit manipulation is based upon, I will talk about it some more. So here you can see, what does this mean in terms of binary? This means that if this is your bit position I, then if you set this as a set bit, if you set this as 1, and even if you were to unset all the bits to the right of it, then this alone, the value of this number is nothing but 2 to the power I, this representation that I have just written. This number alone is more powerful than if you set this to 0 and then you make all of these as 1. Like you are utilizing all of your powers on the right hand side to compete with this single element on the left hand side. So this expression is nothing but this, and this is nothing but this. So you can see that a single element strictly dominates all the elements on its right hand side. So this means that if you set a 1 bit over here, then this element will be strictly greater than x. It cannot be less than or equal to x. So one thing is for sure, that every time you see a 0, you set a 0 over here. Now what happens when you see a 1 over here? Now if you set a 1 over, if you see a 1 over here, you have two choices. You can either set a 0 over here, or let me first set a 1 over here. You can either set 1 and create this number, or you can create this number. Now let's talk about this case first. So in the first scenario, you see that you have made this prefix and this prefix equal. So okay, we'll talk about it some more when we go to the next element. But what about this scenario? Here you have just unset a bit, right? Then again, using that same logic, that 2 to the power I is alone enough to dominate everything on the right hand side. So if you apply that 2 to the power I logic to this index over here, you will notice that since this bit is already set, this means that in this number that you are creating, call it Z, or in fact, let's call it L. This number that you are creating, even if right now you haven't placed any of the bits on the right hand side, but even if you were to place all ones on the right hand side, this number X will still be strictly greater than L. So this means you have entire freedom to do whatever you want on the right hand side, and you will still not violate the constraints of being less than or equal to X. Why? Because you have deviated from the most powerful bit. Like you have already given up your powers by uh, moving from a set bit to an unset bit. So no matter what you do on the lower order bits, you cannot compete with this element. So that is why we call, so this element has a lot of power, wherein you have unset this bit, but this element doesn't have a lot of power. Why? Because why does it not have a lot of power? It will be clear if you look at the next element. Okay, so when you encounter the next element, which is a 0, what does this mean? This means that if you set a 1 over here, then this means that this part and this part was equal, but now this bit alone can dominate everything on the right hand side. So no matter what number that you create, that number will be strictly, so once you have placed 1 over here and call this index I, so this 2 to the power I will be strictly greater than whatever number you create on the right hand side, right? Like had this bit been 0, so this means that placing a 1 over here, after that, no matter what you place on the right hand side, this number will be strictly greater than this number. Why? Because their prefix match, but their highest order bit differs, and this is the first bit that wins. So this can dominate everything that comes on the right hand side. So this means that you cannot place a 0, you cannot place a 0 if the prefix is same. Then you cannot place sorry, if the prefix is same, then if you encounter a 0, you have to place a 0, you cannot place a 1. But remember that this element has a lot of freedom. For this element, you can either place a 0 and you would be fine, but you can also place a 1 and you would also be fine. Why would you be fine? Like, you are not allowed to place a 1 here, but you are allowed to place a 1 at this position. Why is this the case? Because we have already talked about the case that this element has already lost the battle. Why? Because it has already lost on this order bit, right? The highest order bit. And we said that no matter what you do on the right hand side, you cannot compete with this number anymore. So if you cannot compete, why not do anything that you wish, right? So that is why, that is where these terms comes from. So that's why we define two terms as tight and loose. So we say that if you have not lost the battle yet, and by that I mean if you have seen a 1 bit and then decided to move to a 0 bit, this is the point where you have lost the battle. But once you lose the battle, after that you have the entire freedom to do whatever you want on the right hand side, and you will still be less than the original number. But if you have not lost the battle, then you have to tread very carefully. So that's why the upper number is known as the tight numbers and the lower ones are known as the loose numbers. So just to summarize once again, if you had this binary string 1 1 0 0 1 0 1 0 1, then when you are moving from left to right, suppose I create this number 0 0 1 1 0 0 1. Now is this number tight or loose? So this is a tight number. Why? Because you have not lost the battle yet, like you have not placed a 0 in corresponding to a 1 bit over here. So if you are a tight number, then you have to follow the constraints very strictly. This means that every time you see a 0, you have no choice, but you have to place a 0 over here. Otherwise, if you accidentally place 1, you will dominate this number, and that should not happen because you are trying to create a number that is less than or equal to x. So these are the tight elements. So tight elements have one rule, that is if they see a 0, they have to be a 0. But if they see a 1, they have the option to either remain a tight element or convert to a loose element. So for example, if they see a 0, this will be a tight element. But at this point, they have the option to either remain a tight element by choosing to stay with this one, like choosing to have a common prefix. But if they decide to switch this 1 to a 0, then it means they have already lost the battle and now they are loose elements, right? Now this is a loose element. So what do we mean by loose element? This means that at the first point, at the highest order bit where you placed a 0, where you could have placed a 1, after this point you have entire freedom to do whatever you want, and you can rest assured that this number, this loose number, will always be less than or equal to x. In fact, even if you encounter a 0 right after that, you are free to plug in a 1 over here, nobody would care. You are free to plug in a 0, nobody would care. But for the tight numbers, people care. So if it is a 0, you have to plug in a 0 over here. There is no other option. So this is the concept of tight and loose. So tight just means that you have not diverged from the prefix so far. So this means that every time you encounter a 0, you have to place a 0. This is tight. And loose means going from left to right, there will be a point of divergence. So suppose this is where you diverged. This was 1 and you have switched to a 0, and after this point you are free, you are loose, right? And you can do whatever you want, and this resulting number will be less than or equal to x. So now this was the entire concept of tight in bit manipulation. Now let's see how we can use this concept to solve the original problem, which was maximizing the sum when the XOR is fixed. So this time, let us still construct the answer bit by bit, but will not apply the greedy strategy anymore. So you know that there are a total of k integers, right? So let me write down those k integers and let's stack them vertically so that we can visualize what is happening to the XOR. Suppose k is equal to 5. Then you know that you have to build the answer bit by bit. And if you do that, then first of all, you have to start with the highest order bit. And why is this true? This is the highest order bit. Because remember this property that uh, a single high bit dominates all the lower order bits. So even if you are able to set one, even if you are able to set one over here, and even if the cost means setting 0 for the entire thing on the right hand side, you should take this deal, because this number will strictly be smaller than when you set it to 0 and then you have to set all the remaining parts to 1. So that's why we can start with the highest order bit and try to maximize the highest order bit in all of the numbers as much as we can, so that the overall sum stays the largest. And now let me also draw the bit representation of x, bit representation of n. Now at this position, and okay, let's start with the 0 first. If there is a 0 at this bit position, what does this mean? It means that you can have a maximum, you should have an even number of ones over here, so that their XOR is equal to 0, right? 0 indicates you should have even number of ones, even number of ones at that bit position. Why? Because every one should cancel out and XOR is built bit by bit, so that's why there should be an even number. If there is an odd number of ones, then one set bit will remain and that will become the XOR. So that is clear that if you encounter a 0, you have to place an even number of zeros over here. Another thing that you might be confused about is, if you are building it bit by bit, how would we construct the answer? Because you have to maximize this sum, and you know that you cannot deal with sum bit by bit, right? Sums cannot be dealt bit by bit because they overflow, and then one bit affects the other bit, right? So if you have computed the sum for this bit column and you have placed the sum over here, this will have a carry to the next bit column, and then this bit will affect the next one, right? So you will have to remember the carries that are going forward. This is what you might think, but actually there is another technique that I have already discussed in Brain Gym episode 4, where I told you that there is a technique through which you don't have to worry about the carries anymore, and you can treat sum which influences all the bits together as a bit by bit operation. And how do you do that? You do that by this representation. So you say that when you are summing up all the bits at this position, you do not do a carry anymore. You say that, okay, if the sum is s, you say that the contribution, so you apply some contribution technique to this bit, and you say that the contribution of this technique is, contribution of this bit is s into 2 to the power I. So this is the contribution from this bit. So with this contribution technique, you will know that sums can also be dealt with bit by bit, and that's why building the answer bit by bit is the correct strategy over here. We don't have to worry about carries anymore. Now, how do you place an even number of ones? And right now you're allowed to place an even number of ones. But you see that we have already discussed that you are not allowed, if the number is not loose, then you are not allowed to place a 1, right? Because right now at the start all the numbers will be tight. So if you place a 1 over here, even though you have to place an even number of ones, if you place just two ones, then these two numbers will be strictly greater than this number. Why? Because this bit dominates this segment, right? We have already discussed that. So this means that if you see a 0, then you really can't do anything, right? So let's assume that if you see a 0, sure, you had to place an even number of ones, but right now, since this is the first 0 that you are seeing, you have to place zeros in everything. So okay, that's fine. Now what about when you see a 1 over here? Then when you see a 1 over here, you know that you have to place an odd number of ones, right? So that one set bit can remain and the final XOR will be equal to 1. Odd number of ones. What am I even writing? So odd number of ones. And you will realize that you have to place as many ones as possible. Why? Because if you compromise now, then you will lose the battle, right? We already said that this bit dominates everything that is supposed to come on the right hand side. So make the best decision now. Be as greedy as you can. This means that if you are given the possibility of adding an odd number of ones, you can add it in everything. So if the entire, if there are a total of odd number of elements, then you can add one in just all of the elements and be done, because that's what you wanted. But what if the total number of elements is even? If the total number of elements is even, then which is the case over here, 1 2 3 4 5, no, it is actually odd. But let me, for now, let me do this. I will hide it over here, and then you see that the total number of blocks is even. So you place, so right now no numbers are built, so you place 1 1 and 1, and the contribution from this bit is 2 to the power I, whatever this I is, times 3 plus 0 into 2 to the power I, because you have to place a 0 over here. But now notice what happens. Since you have placed 1 over here, these numbers are tight because their prefix are same and they have not diverged. But this number has become loose. So what you do is you keep track of which number has become loose and which numbers are still tight. So this is tight, this is a tight number, and this is also a tight number. Now what happens when you encounter a 0 over here? So if you encounter a 0 over here, like I said, you want an even number of ones. But then you, even though you do want an even number of ones, but 0 means tight bits cannot, tight bits have to, tight numbers have to respect that 0. So if it's a 0, they also have to be 0. So if it is a 0, in all the tight numbers, you have to place a 0. There is no way around it. But on the loose numbers, right? On the loose number, you are allowed to do anything that you want. So you are allowed to place an even number of ones, but where exactly? So this even number of ones will go inside the loose set. So all, you collect all the loose numbers. Suppose there are 20 loose numbers, then in half of those loose number you place a 1 bit, and in other half you place, no, sorry, if there are 20 loose numbers, then in all of those 20 loose numbers you place 1, so that their XOR is still 0. They do not affect the final answer, but their sum is 2 to the power I into 20. So now you see that once a number becomes loose, it gives you a lot of benefits in the future. Although nobody would like to become a loose number. Why is that? Because becoming a loose number means you are already losing the battle at the bigger stage, right? Where things matter most, 2 to the power I. But but somebody has to lose, right? At this position, when he had to place a 1, somebody had to lose. So if this guy has already lost over here at this round, 2 to the power I, then it has the freedom to change the outcome in any way it wants. it can place 0, it can place 1, it can place anything that you tell it to, as long as your conditions for this is satisfied. So this means that suppose you have done the process so far, and let's say you have this sequence 1 1 0 0 1 0 1 1 0 1, and suppose you have processed these many elements so far. Okay, you have processed these many elements so far, so there will be some tight numbers. So assume that there are t tight numbers and then there are l loose numbers that are created from processing the bits from left to right. Now what happens when you encounter a 0? If you encounter a 0, in all the tight numbers you have to keep a 0, you have to retain a 0, so they will not provide any contribution at this bit position. And in all the loose numbers, you want the overall XOR to be equal to 0. So in all the loose number, so suppose the number of loose numbers is equal to 15, then in 14 of them, in 14 loose numbers, you can place 1 and all of them will cancel out. And in one loose number, you can place a 0 so that the XOR can still be 1. So the answer in this case, when you encounter this 0, the answer would simply be, what is the contribution at this location I? So if this is the loose number, so the tight numbers, they have to be 0, so they contribute 0 into 2 to the power I, plus the loose numbers, how much would they contribute? They would contribute L by 2, because no, sorry, not L by 2. You are planning to set all the loose numbers as 1 except maybe 1, right? So if L is even, then all the loose number you can freely set it as 1, because it will be guaranteed that that number will always remain loose. So you can do, if L is even, you could do 0 1 sorry L into 2 to the power I. But if L is odd, you can do 0 into 2 to the power I plus L minus 1 into 2 to the power I. That is, you will miss out on just one loose number, but you can still create this. So this is the case when you encounter a 0. But what if you encounter a 1? So, and after this, you see that there has been no transition. So when you encounter a 0, the number of tight numbers remain the same and the number of loose numbers remain the same. Why is that? Because tight elements can only transfer to the loose set, but they cannot come back. A loose element cannot become a tight element again, but a tight element can become a loose element at some point of time. So this part we have solved. Now let's talk about the case where you encounter a 1 in your journey. So when you encounter a 1, suppose you are dealing with this case and you have T elements in the tight set and you have L elements in the loose set. And notice that you actually don't have to maintain the numbers in the tight set as well as the loose set. You just have to maintain the counts. Why? Because for all of these numbers, the tight set looks similar, although the loose set looks very different, because some of them might have 0, some of them might have 1. But remember that we are taking their contribution and multiplying it by 2 to the power I, so that we don't have to worry about carries and we are going forward. So that's why we don't have to track the numbers anymore. Just their size or their count is more than enough. Just knowing the fact whether a number is tight or loose will help you process the next bit. So if you see a 1, then of course the total number of ones will have to be odd. Total ones is odd. So first of all, your goal should be to maximize the number of ones. So first of all, you will start by placing 1 in all of the number, whether it is tight or loose. Why? Because it is allowed. In 0, it was not allowed to place 1 in the tight numbers. But in 1, it is allowed to place 1 in all the numbers that you want. Right? You place it blindly. You place it just blindly. Then what is the worst that could happen? If this entire count, basically tight plus loose, basically which is k, if this entire count is odd, then you are already good, because you were able to get the maximum contribution of this bit, which is equal to 2 to the power I into tight plus loose, or 2 to the power I into k. You got the maximum contribution, and you also got their XOR as this value. So you are good, life's good. Now, what if this k is even? If k is even, then you know that you have to make some compromise. Like one of these element has to be 0, right? So you have to make a compromise when k is even. So if k is even, one of these elements has to be 0. Now let's divide these into tight and loose sets. So this is the tight set, and this is the loose set. Now if I just asked you, okay, I want to set one number as 0, which one would you set? Someone from the loose set or someone from the tight set? At first you might think that instinctively it makes sense to set one of the loose number as 0. Why? Because loose number have the entire freedom, and it doesn't actually matter what happens to them. So if the contribution is remaining the same, no matter if you set a tight number to 0 or a loose number to 0, then we might as well set the loose number to 0. But this is actually wrong, because setting a tight number to 0 is more beneficial. Because see, if you set a tight number to 0, like if you set this to 0, then what would happen? This tight will migrate to the loose set, right? So going from 1 to 0, this is tight and this is loose. So going from 1 to 0, so see, previously we told you that nobody wants to go from tight to loose. Why? Because nobody wants a unset bit when the original number had a set bit. Why? Because you want to maximize the sum. But if you have to set a 0 bit, then does it even make sense to not do the migration? Because the contribution from this is not changing, no matter whether you set a 0 in the loose number or if you set a 0 in the tight number. But if you set a 0 in the tight number, this will migrate to the loose set, and the next time you encounter a 0, you will have a lot of opportunity to set the remaining bits as 1, right? Previously we discussed that in this 0, all the loose elements have had a lot of freedom, but all the tight elements, they did not have a freedom. So this might seem counterintuitive. First of all, like nobody wants to migrate from tight to loose, so why would we voluntarily move an element from tight to loose if you don't have to? That is the reasoning. But here I'm saying that when it is the opportunity and you have to place one element as 0, you should place a tight element, you should migrate a tight element from tight to loose. And this is because even if you did not do that, then one of these loose elements will become 0. So loose elements, so let's see what happens if you do that operation on the loose element. So if you do that operation on the loose element, let's say you turn it to 0, then the next time any operation arrives, that number still gave that contribution of 2 to the power I, because that number was set as 1, that bit was set as 1. But the next time a 0 would arrive, this number will not have the freedom to turn into 1. Now you might claim that, okay, even if this tight number does not have the freedom to turn into a 1 over here, but it still provided this contribution 2 to the power I over here, right? And this contribution is what matters more. So you might think that if this contribution is what matters more, I will keep all the elements in my tight set as 1 only. I will not do the migration. But my point is that this 2 to the power I contribution you could have gotten even if you did the migration. And why is that? Because you have to compulsorily set an element as 0, right? So you will lose out on 1 2 to the power I contribution, no matter where that loss is coming from. That loss could either come from the tight set, or the loss could either come from the loose set. in either case the loss is identical, loss is same. You are losing 1 2 to the power I, right? Otherwise you would have wanted all 2 to the power I in your set, but now you are losing 1 2 to the power I. So if you are losing and you are guaranteed to lose 1 2 to the power I no matter what, then it's actually better to lose from the tight set so that it can migrate to the loose set and give you better options in the future. So think about this idea some more. Maybe it's a bit confusing, although once you get the hang of it, you will find it very uh, intuitive that every time you get the opportunity and you are forced to do the migration, no, every time you get the opportunity, you should migrate from tight to loose if the cost is same. Like if doing something in the loose set is same and doing something in the tight set is the same cost, and the cost over here is 2 to the power I, you should always do the operation on the tight set so that this tight elements can migrate to the loose set, and then they will become more free in the future. So now we have discussed the strategy because we have covered both the cases. When going from left to right, you either encounter a 0, then in the 0 case, all the tight elements are fixed and all the loose elements will be set to equal to 1 except maybe one element. And in the loose set, in the other case where you encounter a 1, we said that all the tight elements will be set to 1 and all the loose elements will also be set to 1. And if the overall count, tight plus loose, which is equal to k, if that is odd, then you are good, no migration needed. Otherwise migration has to be done by paying a cost of 2 to the power I. So you might as well do the migration from tight to loose instead of just keeping your loose set as it is. So finally we'll look at the code, and I will link down the problem in the YouTube description. You can submit this problem, but keep in mind that the problem on Codeforces that asks you to not just print the maximum sum, but also print the members of the tight as well as the loose set. So that is also not difficult to do. I mean, whatever strategy that we have just discussed, for each for each bit position, you just want to iterate over the tight set and the loose set, and then you want to do some transfer. So you can do some transfers here and there, although it's a bit of a case work. So if you don't want to implement the part where you are required to print the actual elements in the tight and loose set, you could just copy one of the templates that I will link below, and in that template you can rely on that person's submission to print the answer, and then you can implement your own solve function that just returns the maximum sum, and you can compare whether both of your answers match or not. So let's look at the code for this problem. So as we discussed, you go from left to right, from higher order bits to lower order bits, and you keep track of the tight count and the loose count. All the elements in the tight set, which is your tight count. Initially, all the elements start from the tight set and nothing in the loose set yet. Then when you encounter a set bit, if you encounter a set bit, then you have to take all the, first of all, you set 1 in all the positions. So that's why all the positions contribute 2 to the power I. You first blindly place 1 in all of the position, and then if k is odd, then you are good. But if k is even, then you have to take one set bit from one of the position. So it is actually preferable to take it from the tight set. So if k is even, then you give this cost, which is 2 to the power I, and if the tight set still exists, you move one number from the tight set. So that's why you decrease the tight set count by 1 and you increase the loose set count by 1. So you increase this loose set count by 1. This is when you encounter a 1. And the second case is when you are going from left to right, if you encounter a 0. So if you encounter a 0, your tight set cannot contribute anything because they also have to be 0. So tight set have to respect the tight constraints. Loose set can do anything. So if you encounter a 0, in the loose set, you blindly place 1 everywhere. So they will contribute 2 to the power I into the number of elements in the loose set. And maybe you might have to revert your change for at most one element if the number of loose set, if the number of elements in the loose set is odd, if it is odd, then it means that the XOR is becoming 1, but you want the XOR to be equal to 0. So if the number is odd, then you like undo your operation. You had set everything as 1, right? You subtract 2 to the power I, and finally this is your answer. Why is this your answer? Because for each element I, you have taken the contribution 2 to the power I, so that's why you did not have to worry about carry. So you see that the code is so simple, just a couple of lines of code, but the logic maybe might not be so simple. So this idea of this tight and loose, I think this is a very basic idea in competitive programming and lead code. But if you are not aware of this, I hope that this video helped you learn some new technique.